Good morning, all of you. Today I am going to make an audio recording for visually impaired student of organic chemistry book of Dr. J.M. Sagal, modern book. Name of the chapter is Alkanes. Introduction. The simplest organic compound are hydrocarbon, the compound containing only carbon and hydrogen. Depending upon the framework of carbon atom in their molecules, the hydrocarbon may have either open chain and ring structure. In addition, they may be saturated or unsaturated in character according to the nature of carbon-carbon bond in them. Due to these variations, hydrocarbons have been divided into different classes. We shall discuss the various classes of hydrocarbon one by one, starting with alkane and cycloalkane. Structures of alkane. Alkanes are open chain structure hydrocarbon having the general formula CnH2n plus 2, where n is the number of carbon atom. They contain only single covalent bond between carbon and carbon, carbon and hydrogen in their molecules. As such, each carbon atom is bonded to 4 other atoms, as is clear from the formula of methane, ethane, propane and the first 3 members of alkane. The bond in alkanes are formed by the overlapping of sp3 hybridized orbital of each carbon atom with similar orbital of other carbon atom or 1s orbital of hydrogen atoms. As the result, all the 4 bonds linking the carbon atom with other atom are sigma bonds. As these bonds are quite strong and are not easily attacked by other reagent, alkene do not react with usually laboratory reagent under ordinary conditions. That is why they are termed as saturated hydrocarbon or paraffins. Latin parum is equals to little, affins is equals to affin. It may also be noted that due to sp3 hybridization of the carbon atom of alkanes, the 4 bonding orbital of each carbons are directed towards the 4 corner of a tetrahedron. For instance, let us consider the case of methane. The simplest alkane, in the formation of its molecule, the 4 sp3 orbital of only carbon atom overlap the 1s orbital of 4 hydrogen atom, which are situated at the corners of tetrahedron, as shown in figure 4.1a. Figure 4.1b represents a molecular model of methane. Figure 4.1c is a simplified 3-dimensional representation of the molecule. In this representation, the wedge represents the bone pointing towards the observer out of the plane of the paper. The hatched line represents the bone going away from the observer behind the plane of the paper, and the normal line shows the bond in the plane of paper. Each carbon-hydrogen bond has a length of 110 pm or 1.10 angstrom, and each hydrogen single bond carbon single bond hydrogen angle is 109 degree 28 minute, which is shown in figure 4.1d. Similarly, in case of ethane, figure 4.2, and higher alkane, the relative arrangement of bond is always tetrahedral, although the different bond angle may be slightly different from the regular tetrahedral value of 109 degree 28 minute. The carbon-hydrogen bond length is about 110 pm or 1.10 angstrom, while the carbon single bond carbon bond length is 154 picometer or 1.54 angstrom or nearly so. On account of the tetrahedral arrangement of 4 bonds formed by each carbon atom, the molecules of alkanes are 3-dimensional in nature. Moreover, in case of alkanes containing more than 2 carbon atoms, the carbon atom of the chain do not actually lie along a straight line. This is quite obvious from the model of propane shown in figure 4.3. In fact, for higher alkane, the carbon-carbon chain can assume a variety of zigzag shape, but for the sake of convenience, the carbon atoms are written in straight line so far as possible to have a planar representation as shown below. Methane, ethane, propane. Classification of carbon atom in alkanes. The carbon atom present in alkane can be divided into 4 categories as given below. Primary carbon atom. It is the carbon atom which is linked directly to either one or no carbon atom. Second, secondary carbon atom 2 degree. It is carbon atom which is linked directly to 2 carbon atom. Third, tertiary carbon atom. It is the carbon atom which is linked directly to 3 carbon atom. Fourth, quaternary carbon atom. It is a carbon atom which is linked directly to 4 carbon atoms. For example, in the formula given below, there are 5 primary, 1 secondary, and 1 tertiary and 1 quaternary carbon atom. Hydrogen atom are also classified as primary, secondary and tertiary according as they are linked to a primary, secondary and tertiary carbon atom respectively. Thus in the example given above there are 15 primary hydrogens, 3 each of on the 5 CH3 group, 2 secondary hydrogen on the CH2 group and 1 tertiary hydrogen on the CH group. Nomenclature of alkanes. The common and IUPAC system of naming the saturated hydrocarbon are discussed below. The common system. According to this system, the first 4 members of saturated hydrocarbon have special name while the higher members are named according to Latin or Greek numerical indicating the number of carbon atom in the molecule. The name of all the members N is ane, thus CH4 is methane, C2H6 is ethane, C3H8 propane, C4H10 butane, C5H12 pentane, C6H14 hexane, C7H16 heptane, C8H18 octane, C10H22 decane, C20H42 ecosane. In case of isomeric alkene from C4H10 onwards, the following distinctions are made in naming the various isomers. First, the hydrocarbon having all the carbon atom in the straight or continuous chain are termed normal or N-hydrocarbon. For example, CH3, CH2, CH2, CH3 is called N-butane, while CH3, CH2, 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 CH3 is named as N-pentane. Second is branched chain isomer having a tertiary carbon atom are known as iso, while those containing a quaternary carbon atom are named neo. For example, CH3, CH, CH3, CH, CH3, isobutane, CH3, CH2, CH, CH3, CH3, isopentane. Second is neopentane. Alkyl groups. The removal of one hydrogen atom from a molecule of an alkane gives a monovalent group called alkyl group. It has the general formula CnH2n plus 1 and is usually represented by the letter R. The names of alkyl group are obtained by replacing the suffix "ane" of the name of corresponding alkane by L. It may be possible to get more than one alkyl group from an alkane depending upon the position of carbon from which hydrogen is removed, as illustrated below. Name and formula of alkane. Methane CH4, CH3 methyl, ethane CH3CH3, CH3CH2 is ethyl, propane CH3CH2CH3, one hydrogen replaced, then CH3CH2CH2 is N-propyl, and secondary hydrogen is replaced, then it is called isopropyl. And butane CH3CH2CH2CH3, 1 degree hydrogen replaced, then it is called N-butyl. 2 degree hydrogen is replaced, then it is called secondary butyl, and 1 degree hydrogen is replaced, then it is called isobutyl. Isobutane CH3CH, CH3CH3. If 3 degree hydrogen is replaced, then it is called tertiary butyl. IUPAC system. Straight chain alkanes. The alkanes in which all the carbon atoms are present in straight chain are named by adding the suffix "ane" to the appropriate word root. For example, methane, ethane, propane, butane. Branch chain alkane. In case of branched chain alkane, the largest possible continuous chain of the carbon atom is selected. The corresponding word root followed by the suffix "ane" is written down. The chain is numbered from the end, which gives the lowest number to the carbon carrying the substituent alkyl group. If the number of substituent group is more than 1, numbering is done from the end according to the lowest set of locants for the branching alkyl group. The name of branching alkyl group along with their branchment numbers are then prefixed before the word root in alphabetical order as illustrated below. 2-methyl propane, 2-methyl butane, 2,2-dimethyl propane. 4-ethyl 2,2-dimethyl hexane, 4-ethyl 3,6-dimethyl octane. Some important points for giving IUPAC names. A few important points to be remembered for IUPAC names of alkane are given below. First, if two different alkyl groups are equidistant from the two ends of the parent chain, the numbering of the chain is done in such a way that the group which come first in alphabetical order get the lowest number. For example, 3-ethyl, 6-methyl octane. Since ethyl comes ahead of methyl in alphabetical order, the parent chain is numbered from the end, which gives the lowest number to ethyl group. Second, if the group attached to the parent chain is also branched, sometimes called complex substituent, it is named as substituted alkyl group by separately numbering the carbon atom of this group. For this purpose, the carbon atom of this group which is attached to the parent chain is always numbered as 1. The name of such group is always written in bracket. For example, 7-ethyl, 2-methyl, 5, bracket start, 2-methyl propyl, nonane. Third, for deciding their alphabetical order, the complete name of the complex substituent including the prefix such as di, tri, forming the part of the name is considered. For example, 5,1,2 dimethyl butyl, 7-ethyl, 2-methyl decane. The alphabetical order of the name of complex substituent is decided on the basis of letter D, which is the first letter of the complete name of this group. Fourth, while naming a compound, if two equally long chains are possible but the number of side chains attached to each possible chain are different, the possible chain having largest number of side chain is selected as the parent chain. For example, 3,5 diethyl 2,4 dimethyl octane. Correct parent chain since it has 4 side chain. Second is incorrect parent chain since it has only 3 side chains. Structural isomers in alkanes. Each of the first 3 members of alkane, methane, ethane, propane, can have only one structural formula. This is methane, ethane, propane. However, the higher member from butane onward can be represented by more than one structural formula and then exhibited structural isomerism. The various isomers of the some hydrocarbon differ in the framework of the chain of carbon atom and therefore isomerism exhibits by alkane in terms of chain isomerism. For example, butane C4H10 exists in the form of two isomers shown below, N-butane or butane, isobutane or 2-methyl propane. Similarly, pentane C5H12 exists in the form of 3 isomers, N-pentane or pentane. Second is isopentane or 2-methyl butane. Third is neopentane or 2,2-dimethyl propane. C6H14 exists in the form of 5 isomers. C7H16 has 9 isomers and C8H18 has 18 isomers and so on. Natural sources of alkanes. Petroleum, which occur naturally below the surface of Earth, is a mixture of many hydrocarbons, most of which belongs to alkane series. Natural gas, which issues from petroleum field, and fuel gas obtained from coal contain lower alkanes. The waxy constituent of some plants have also been found to contain alkanes. For example, pine wood and turpentine oil contain N-heptane, while the leaves of cabbage contain N-nonocosane. C29H16. General method of preparation. The preparation of alkane by synthetic method is only rarely carried out. The usual practice is to isolate these hydrocarbons, particularly the lowest one, from some suitable natural sources. However, some of the general methods which can be employed for their preparation are discussed below. First, hydrogenation of unsaturated hydrocarbon, Sabatier-Sandrance reaction. Alkanes or alkynes can react with halogen in presence of catalyst, finally divided nickel, platinum and palladium to form alkanes. Alkane plus H2 give rise to CnH2n plus 2 in the presence of nickel or 525 or 575 Kelvin temperature. Ethylene in the presence of nickel 525 to 575 Kelvin gives rise to ethane. Alkyne in the presence of nickel or 525 to 575 Kelvin temperature give rise to CnH2n plus 2. For example, acetylene in the presence of nickel or 525 to 575 Kelvin temperature give rise to ethane. The use of nickel as catalyst for hydrogenation requires a temperature of about 525 to 575 Kelvin, but if platinum or palladium is used as catalyst, the reaction can take place even at room temperature. Methane cannot be prepared by this method as the starting alkane or alkyne must contain at least 2 carbon atoms. Second is reduction of alkyl halide. Alkyl halide can be reduced directly or through the formation of Grignard reagent to form alkanes. First is direct reduction. The direct reduction of alkyl halide is generally carried out with chemical reducing agents such as zinc and hydrochloric acid or zinc copper couple or alcohol or with hydrogen in the presence of palladium catalyst. Alkyl halide in the presence of ZnH positive give rise to alkanes plus HX. N-butyl bromide in the presence of ZnH positive give rise to N-butane plus HBr. Isopropyl chloride in the presence of palladium give rise to N-propane plus HCl. The reduction may also be carried out by heating the alkyl halide, particularly iodides, with hydrogen iodide in the presence of red phosphorus in a sealed tube. For example, ethyl iodide plus Hi in the presence of red phosphorus give rise to ethane. Second is reduction through the formation of Grignard reagent. This is an indirect method of reducing alkyl halide. A solution of alkyl halide in dry ether is treated with magnesium to form an ethereal solution of alkyl magnesium halide, commonly known as Grignard reagent. Alkyl halide plus Mg in the presence of dry ether give rise to alkyl magnesium halide or Grignard reagent. The Grignard reagent are easily decomposed by water producing alkanes. Grignard reagent plus HOH give rise to alkane plus MgOXH. Methyl magnesium iodide plus HOH give rise to methane plus MgOHX. It may be pointed out that the alkene and alkyl halide used for the preparation of alkane by the above mentioned method are themselves generally obtained from alcohol. But the alcohol cannot be directly converted with alkane as the hydroxy group of most alcohol resists reduction to corresponding alkanes. Third is Wood's reaction. This reaction brings about the union of two alkyl radicals by the action of metallic sodium upon alkyl halide in dry ether. The resultant product are alkene with a carbon skeleton having higher number of carbon atoms than the reacting alkyl halide. Alkyl halide plus 2 sodium plus X are in the presence of dry ether give rise to alkane plus 2 NaI. Methyl iodide plus ICH3 plus 2 Na in the presence of dry ether give rise to ethane plus 2 NaI. Ethyl bromide plus 2 Na plus BrCH3 CH2CH3 in the presence of dry ether give rise to N-butane plus 2 NaBr. It may be noted that when the reaction involves two molecules of same alkyl halide, a symmetrical alkane RR having an even number of carbon atoms is formed. For preparing an unsymmetrical alkane containing 3 or more than 3 carbon atoms, for example propane, a mixture of different alkyl halide has to be used. Methyl bromide plus 2 Na plus Br plus CH2CH3 in the presence of dry ether gives rise to propane plus 2 NaBr. But the product obtained by using different alkyl halide consists of a mixture of alkane which cannot be easily separated. This is because the two alkyl halide also react separately with the sodium to form two more hydrocarbons as product of the side reaction. Thus, in case of above reaction, ethane from CH3Br and sodium and butane from C2H5Br and sodium are also obtained. The main feature of Wood's reaction is that it leads to the formation of carbon-carbon bond. As such, the reaction can be employed for preparing compound containing higher number of carbon atoms from those containing lesser number of carbon atoms. For example, ethane can be prepared from methane as follows: CH4 plus Cl to give rise to CH3Cl plus HCl, CH3Cl plus 2Na plus Cl, CH3 give rise to CH3CH3 plus 2 NaCl. The order of reactivity of different alkyl halide in this reaction is iodides, bromides, chlorides. Limitation of Wood's reaction. First, it is suitable only for the preparation of symmetrical alkane RR. It cannot be used for the preparation of methane. Third is tertiary alkyl halide cannot be used in this reaction. Mechanism. Two mechanisms have been suggested for this reaction. These are first, intermediate formation of free radical. According to this mechanism, it is believed that the alkyl halide first form alkyl radical which combine with another to furnish the hydrocarbon. Thus, Rx plus sodium give rise to R radical plus NaX. R radical plus R radical give rise to RR hydrocarbon. This mechanism operates when the reaction is carried out in vapor phase. Second, intermediate formation of an organometallic compound. Here the reaction is believed to take place through the formation of organometallic compound as intermediate. For example, Rx plus 2 sodium give rise to Rna plus NaX. Rna plus Xr give rise to Rr plus NaX. This mechanism operates when the reaction is carried out in the solution. Fourth, Core-House synthesis. This method was developed around 1970 as is much better method than Wood's reaction for preparing alkane containing higher number of carbon atom than the reactant taken. It consists of reaction between an alkyl halide and a lithium dialkyl copper. Alkyl halide plus lithium give rise to alkane plus LiX. Dialkyl copper. R and R dash may be same or different. For example, N-butyl bromide plus lithium dimethyl copper give rise to N-pentane plus methyl copper plus LiBr. Lithium dialkyl copper required in the reaction is itself prepared from alkyl halide as illustrated below. Rx plus 2 lithium give rise in the presence of diether give rise to RLi plus LiX. 2RLi plus CuX give rise to R2Cu Li plus LiX. To obtain good yield of alkanes, alkyl halide used is generally a primary alkyl halide, while the alkyl group in lithium dialkyl copper may be primary, secondary or tertiary. An important feature of this reaction is that it can be used for preparing all type of alkanes, whether symmetrical or unsymmetrical, whether straight chain or branch chain mechanism. In the beginning, the alkyl group or alkyl lithium displays halogen from copper halide to form alkyl copper. RLi CuX give rise to alkyl copper plus LiX. Alkyl copper react further with alkyl lithium to form lithium dialkyl cuprate. LiR plus Cur give rise to bracket start R2Cu bracket close negative sign Li positive. Alkyl halide then undergo nucleophilic attack by dialkyl cuprate anion to generate an unstable intermediate which decomposes to give the final product. R2Cu plus R-X give rise to bracket start R2Cu R double dash X bracket close negative give rise to R dash plus RCu plus X negative. Cole's electrolytic reaction. In this reaction, concentrated aqueous solution of sodium or potassium salt of monocarboxylic acid is subjected to electrolysis to get alkanes. 2RC double bond O Na plus 2H2O give rise to alkanes plus 2NaOH plus H2. The reaction takes place as follows. Sodium salt of the acid, equilibrium sign 2RC double bond O negative plus 2Na positive. 2RC double bond O negative 2 electron give rise to 2RC double bond O give rise to RR plus 2CO2 at the anode. 2H positive plus 2 electron give rise to H2 at the cathode. The discharge potential of H positive ion is lower than that of Na positive ion. Therefore, H positive ion are discharged at the cathode, liberating H2, while Na positive ion remain in the solution. For example, sodium ethanoate or sodium acetate, equilibrium sign CH3C double bond O negative plus 2Na positive, 2CH3C double bond O negative, 2 electron give rise to 2CH3 C double bond O give rise to ethane plus 2 CO2 at the anode. 2 H positive plus 2 electron give rise to H2 at the cathode. This is good method for preparing ethane and higher alkane having even number of carbon atom. Methane cannot be prepared by this method. Sixth, decarboxylation of monocarboxylic acid. When heated with soda lime, NaOH plus CaO, sodium salt of monocarboxylic or fatty acid undergo decarboxylation to form alkanes. The reaction involves the elimination of carbon dioxide from carboxylic group. Active component of soda lime in this reaction is NaOH, but it is not employed as such because it melts on heating and is deliquescent as well. Sodium salt of fatty acid plus NaOH in the presence of CO give rise to alkanes plus Na2CO3. For example, sodium acetate plus NaOH give rise to methane plus Na2CO3. Oakwood and co-workers 1950 have shown that the reaction proceeds according to above equation only in the case of sodium acetate. In case of higher member, various side products are also obtained. Thus, in this reaction, sodium propionate, the reaction gives methane, hydrogen and certain unsaturated hydrocarbon also in the addition to ethane. It may be pointed out that alkanes are also formed during some other chemical reaction, but these reactions are not employed for the actual preparation of alkane either because of the poor yield of desired product or some other drawbacks. Preparation of methane. Beside methods number 2, 4, 6 described above, methane can also be prepared conventionally by dropping water over aluminium carbide. Aluminium carbide plus 12H2O give rise to 4AlOH3 plus methane. The gas obtained by this method is generally contaminated with hydrogen and acetylene. Preparation of ethane. Although ethane can be prepared by any of the general method of preparation, it is generally prepared in the laboratory by the reduction of ethyl iodide or ethyl bromide with nascent hydrogen produced by the action of zinc-copper couple on ethyl alcohol. Ethyl alcohol plus zinc in the presence of copper give rise to zinc ethoxide plus 2H. Ethyl iodide plus 2H give rise to CH3CH3 plus Hi. Physical properties of alkanes. Physical state. The lower member of alkane containing up to 4 carbon atom are colorless gases. The higher number alkane having 5 to 7th carbon atom are colorless liquid, and beyond that they are colorless solid at room temperature. Second, boiling point. The boiling point of an alkane increases regularly with the increasing number of carbon atoms. There is an increase of about 20-30 degree for each carbon atom added to the chain except in the few first cases where the increase is much more. This can be explained in the term of intermolecular forces of attraction. Alkanes are non-polar compound having weak van der Waals forces of attraction between their molecules. These forces act along the surface of molecules and their magnitude increase with increase in the surface area. As the molecular size of alkane increases, the surface area and the strength of van der Waals forces also increase. As a result, the boiling point also increase. Amongst the isomeric alkane, there are small differences in the boiling point of various isomers. The branch chain have invariably lesser boiling point than the normal compound, and the greater the branching, the lower is the boiling point of the branched isomer. For instance, the boiling point of N-pentane, isopentane and neopentane are 309, 301 and 282.5 Kelvin respectively. This is due to the fact that branch isomers are more compact. It means they have lesser surface area than their normal counterparts. Due to lesser surface area of such molecules, the van der Waals force of attraction operating between them are comparatively weaker. As such, lesser energy is needed to overcome these forces for the boiling point to take place, and therefore their boiling point are lower. Third is melting point. The melting points of alkane do not show a very smooth gradation with the increase in molecular size. For instance, let us consider the melting point of N-pentane to N-octane. Melting point of N-pentane is 85.9. Melting point of N-butane is 138 degree. Melting point of N-pentane is 143.3. Melting point of N-hexane is 179, melting point of N-heptane is 182.5, and melting point of N-octane is 216.2. It may be seen that increase in melting point is much more in moving from an alkene having odd number of carbon atom to higher alkane than in moving from the alkene having even number of carbon atom to the higher alkane. This is essentially because the intermolecular forces in a crystal not depend only upon the size of molecule but also depend how well the molecule fit into the crystal lattice. It has been already made clear that carbon in alkane form zigzag type of chain rather than straight chain. Now in alkane containing an even number of carbon atom, the terminal methyl group lie on the opposite sides of the zigzag chain. On the other hand, in case of an alkene having odd number of carbon atom, the terminal methyl group lie on the same side of the chain as shown below. N-hexane, even number. Second is N-heptane, odd number. It appears that the alkane having an odd number of carbon atom do not fit in so closely together in the crystal structure as the alkane having an even number of carbon atom. As a result, the energy required to break the crystal structure and thus melts the alkane is lesser in case of alkane having odd number of carbon atom. That is why they have lesser than expected melting point as shown by only a slight increase in melting point in moving from an even number alkene to a higher odd number alkane. Fourth is specific gravity. The specific gravities of alkane also increase with increasing molecular weight but become constant at about 0.8. This implies that all alkanes are lighter than water. Solubility. Due to nearly some same electronegativities of carbon and hydrogen atom present in them and the symmetrical shape of their molecule, alkane are non-polar in character. As such, they are insoluble in polar solvents such as water but dissolve freely in non-polar solvent such as ether. The solubility is decreased with increase in molecular weights. Chemical properties. The molecular structure of alkane involves only carbon-carbon and carbon-hydrogen single bond. As all these bonds are sigma bonds and are practically non-polar in nature, alkane constitute a rather unreactive class of compound. They are quite inert towards the common reagents such as acid, alkyls, and oxidizing or reducing agent under ordinary condition. However, under strong condition, alkane do undergo a few reactions mostly involving substitutions. The reactions generally take place by free radical chain isomerism. The important reactions of alkane are described ahead. First is halogenation. This reaction involves the replacement of one or more hydrogen atom of an alkane by a corresponding number of halogen atom. Chlorination or bromination are carried out by treating the alkane with chlorine or bromine in the presence of light, sunlight or ultraviolet light, or at high temperature 525 to 673 Kelvin. For example, when chlorine reacts with methane under these conditions, all the 4 hydrogen atoms of methane can be successfully replaced by chlorine atom as shown below. Methane plus Cl2 give rise to methyl chloride plus HCl. CH3Cl plus Cl2 give rise to methylene chloride dichloromethane plus HCl. CH3Cl plus Cl2 give rise to CHCl3 chloroform trichloromethane plus HCl. CHCl3 plus Cl2 give rise to CCl4 carbon tetrachloride tetrachloromethane plus HCl. Bromination, though similar to chlorination, take place less readily. Iodination. Iodination of alkane is extremely slow and reversible. CH4 plus I2 equilibrium sign CH3I methyl iodide plus HI. Therefore, direct iodination of alkane cannot be brought about. However, the necessary may be carried out in the presence of oxidizing agents such as iodic acid, nitric acid, etc., which convert the hydrochloric acid product into iodine. 5HI plus HiO3 give rise to 3I2 plus 3H2O. Fluorination. Fluorination of alkane is not generally carried out because it takes place with explosive violence. Moreover, fluorination often involves extensive rupture of carbon-carbon as well as carbon-hydrogen bond. The reaction can be made less vigorous by diluting fluorine with an inert gas such as nitrogen or argon. It is obvious therefore that in order of reactivity of halogen towards alkane is fluorine, chlorine, bromine and iodine. Halogenation of higher alkanes. Formation of isomeric halogen derivatives. The halogenation of higher alkane yield a mixture of all possible isomeric halogen derivatives. For example, chlorination of propane give a mixture of 1-chloropropane and 2-chloropropane. Further chlorination gives a mixture of 4 substitution products which are shown below. 1,1-dichloropropane, 1,3-dichloropropane, 1,2-dichloropropane, 2,2-dichloropropane. The mechanism of halogenation is discussed a little later. Note: it may be seen that halogenation of alkane is an oxidative process because it involves replacement of electropositive hydrogen atom by electronegative halogen atom and is accompanied by an increase in the oxidative state of carbon. Nitration. This reaction involves the substitution of a hydrogen atom of an alkane by a nitro group. This is carried out by heating the hydrocarbon in the vapor state with nitric acid at about 700 Kelvin. Alkane plus HNO3 at the presence of 700 Kelvin temperature give rise to nitroalkane plus H2O. During nitration, rupture of carbon-carbon bond in some of the molecule also take place. As a result, the reaction furnishes a mixture of different products. For example, the nitration of propane results in the formation of a mixture of 4 nitro compounds as shown below. CH3, CH2, CH3 plus HNO3 give rise to 1 nitropropane, 2 nitropropane, nitroethane, nitroethane. Sulfonation. It is the reaction involving the replacement of a hydrogen atom of an alkane by a sulfonic acid group. Only a higher alkane undergoes sulfonation by the reacting with fuming sulfuric acid. For example, hexane plus H2SO4 in the presence of SO3 give rise to hexane sulfonic acid plus H2O. Nitration and sulfonation are believed to take place by free radical mechanism. Oxidation. First, combustion. When burnt in excess of air or oxygen, alkane undergo complete oxidation to produce carbon dioxide, water and large quantities of heat. CnH2n plus 2 plus O2 excess give rise to NCO2 plus N plus 1 H2O plus H2 heat. For example, CH4 plus 2 O2 give rise to CO2 plus 2 H2O. Delta H is equals to minus 890 kilojoule. 2C2H6 plus 7O2 give rise to 4CO2 plus 6 H2O. Delta H is equals to minus 3110 kilojoule. In spite of being highly exothermic reaction, combustion requires a higher temperature, that of a flame, to start it. This is due to the energy of activation required to initiate the reaction. Due to the large quantities of heat produced during combustion of alkane, this reaction have tremendous practical importance. Vast quantities of hydrocarbon obtained from petroleum are used as fuel for the production of heat and power by combustion. The cooking gas, commonly known as LPG, liquefied petroleum gas, is a mixture of propane and butane compressed as liquid. Incomplete combustion. Incomplete combustion of alkane due to insufficient supply of air or oxygen result in the formation of soot or carbon black. This is used in the manufacture of Indian ink, printer ink, black varnish, and as a filter for rubbers. Catalytic oxidation. When heated in a regulated supply of air or oxygen at higher pressure in the presence of a suitable metallic catalyst, lower alkene are oxidized to alcohol and aldehyde, while higher homologous yields long chain fatty acid. For example, when a mixture of methane and oxygen in suitable proportion is compressed to 100 atmosphere and passed through copper tubes at 475 Kelvin, methane is oxidized to methanol. 2CH4 plus O2 in the presence of 475 to 100 atmosphere in the presence of copper tube give rise to 2CH3OH. When a mixture of methane and oxygen is passed through heated molybdenum oxide, methane is oxidized to formaldehyde. CH4 plus O2 in the presence of MO2O3 HCHO plus H2O. Third, Normally, alkane resists the action of oxidizing agents such as potassium permanganate, but alkane containing tertiary hydrogen atom can be oxidized by such reagent to corresponding alcohol. For example, isobutane plus O in the presence of alcoholic KMnO4 give rise to tertiary butyl alcohol. Fifth, thermal decomposition or pyrolysis. This process involves the decomposition of bigger molecule into a number of simple molecule by the action of heat. When heated to about 775 to 1075 Kelvin, higher alkene undergo pyrolysis to yield smaller molecule. For example, propane decomposes as follows at about 735 Kelvin. Propane 735 first product is ethylene plus methane 55% and second product is propylene plus H2 45%. It is apparent that pyrolysis involves the decomposition of carbon-carbon as well as carbon-hydrogen bond. The decomposition of product depends upon the nature of starting compound and the condition employed. The pyrolysis or thermal decomposition of alkane obtained from petroleum is commonly referred to as cracking or fragmentation. Cracking is very important process from commercial point of view and is discussed in detail under petroleum. Sixth, catalytic reforming or aromatization. This process concerns the conversion of aliphatic hydrocarbon into aromatic hydrocarbon in the presence of suitable catalyst. The reaction involves dehydrogenation, cyclization, and even isomerism in some cases. It is generally carried out at high temperature of about 720 to 820 Kelvin, higher pressure 10 to 20 atmospheres, and in the presence of a catalyst when generally consists of chromic oxides spotted on aluminium oxide. Thus, N-hexane changes into benzene and N-heptane changes into toluene. N-hexane in the presence of 770 Kelvin, 10 to 20 atmosphere, CrO3, aluminium oxide give rise to benzene plus 4H2. N-heptane in the presence of 770 Kelvin, 10 to 20 atmosphere, Cr2O3 or Al2O3 give rise to toluene plus 4H2. These days, the reaction is generally carried out at 670 Kelvin in the presence of platinum as a catalyst. Therefore, the reaction is also sometimes termed as platforming. Isomerization. It is the process of converting one isomer into another. It is found that when an alkane is heated in the presence of aluminium chloride and hydrogen chloride, they are converted into branch chain isomers. For example, N-hexane in the presence of 375 Kelvin, AlCl3 or HCl give rise to 2-methylpentane plus 3-methylpentane. Mechanism of halogenation of alkane. Mechanism of halogenation. The halogenation of alkane is known to be free radical chain reaction. This is because it is proceed through a series of steps involving free radicals, each step generating a free radical that bring about the next step till the chain of these steps is finally broken. These are three fundamental stages of chain reactions, namely first, chain initiation step, chain propagating step, C. Chain terminating step. Let us discuss the mechanism of halogenation by considering the chlorination of methane. A. Chain initiation step. The reaction is initiated by the homolytic cleavage of chlorine molecule into two chlorine atom or free radical, each carrying an odd or unpaired electron. The energy required for this is supplied by heat or light. ClCl in the presence of heat 523 to 673 Kelvin or light give rise to 2Cl radical. Chain initiating step. B. Chain propagating step. Once the chlorine atom or free radical are formed, each of them react with a methane molecule forming hydrochloric acid and generating a methyl free radical as shown in figure 2. Each of the methyl radical in turn react with another chlorine molecule to form methyl chloride. and at the same time generates another chlorine molecule atom or free radical as shown in step 3. This newly formed chlorine atom can react with another molecule of methane as shown in step 2 to produce another molecule of hydrochloric acid and another methyl free radical. The methyl free radical can again repeat the step 3 and so on. Thus the step 2 and 3 are repeated several times and the chain gets propagated till it ultimately terminated. Second, 2CH3H plus Cl radical give rise to HCl plus CH3 radical. Third, CH3 radical plus ClCl give rise to CH3Cl plus Cl radical. Chain propagating step which are repeated several times. The chlorine atom formed in step 3 can also react with the methyl chloride formed to yield hydrochloric acid and a new substituted methyl radical as shown in step 4. The substituted methyl radical would react with another molecule of chlorine to form dihalogenated methane as indicated in step 5. Theoretically, this process may extend further till all the replaceable hydrogen atom in the methane molecule have been substituted by chlorine. Step 4. Cl radical plus CH3Cl give rise to HCl plus CH2 radical Cl. Fifth step. ClCl plus CH2 radical Cl give rise to CH2Cl2 plus Cl radical. Sixth. Cl radical plus HCHCl2 give rise to HCl plus CH radical Cl2. 7. ClCl plus CH radical Cl2 give rise to CHCl3 plus Cl radical. 8. Cl radical plus HCCl3 give rise to HCl plus CCl3 radical. 9. ClCl plus CCl3 radical give rise to CCl4 plus Cl radical. C step. Chain terminating step. The chain of the reaction initiated and propagated as outlined above may be terminated if the free radical combine among themselves without giving rise to any new radical as shown below. C radical plus C radical give rise to Cl2. CH3 radical plus CH3 radical give rise to CH3Cl. CH3 radical plus CH3 radical give rise to CH3CH3. The chances of free radical combining among themselves are very indeed because of the very small relative concentration of free radicals in the reaction mixture. Still, such a combination cannot be completely ruled out. As this happens, the chain of step initiated by the cleavage of a particular chlorine molecule comes to an end, but other similar chains initiated by other chlorine molecule continue to operate and therefore the overall reaction keeps on progressing. Evidence in support of the above mechanism. The free radical mechanism of halogenation is supported by the following fact. First, the reaction does not take place in the dark at ordinary temperature but require energy in the form of heat 525 to 675 Kelvin or heat light to initiate the process. This is because the reaction initiating step involves the dissociation of halogen molecule into free radical which required for the supply of energy. Second, high quantum yield. For each photon of energy absorbed, many thousand molecule alkyl halide are formed. This is evidently due to the repeating chain propagating step. Third, it has been observed that addition of substances that are sources of free radical can initiate the reaction in dark at the temperature below 525 Kelvin. For example, in the presence of 0.02% of tetraethyl lead C2H5 bracket 4 Pb, chlorination of methane proceed in the dark at 415 Kelvin. CH4 plus Cl2 in the presence of 415 Kelvin 0.02% C2H5 4 Pb give rise to CH3Cl plus HCl. It is also known that at 415 Kelvin, tetraethyl lead decomposes to give metallic lead and ethyl free radical. C2H5 4 Pb in the presence of 415 Kelvin give rise to Pb plus 4 C2H5 radical. It appears quite reasonable that the ethyl radical formed in this manner attack chlorine molecule to produce chlorine atom or free radical. C2H5 radical plus Cl Cl gave rise to C2H5Cl plus Cl radical. The chlorine atom thus generated then start the chain propagating step and the reaction progresses. Similarly, the reaction proceed at lower temperature in the presence of benzyl peroxide because it generates free radical at lower temperature. Fourth, role of inhibitors. An inhibitor is a substance that can slow down or although stops a reaction even when present in small quantities. It has been observed that oxygen acts as an inhibitor in the halogenation of alkane. This is believed that due to the fact that an oxygen molecule combines rapidly with an alkyl radical to form the comparatively much lesser reactive peroxyl alkyl radical ROO radical. R radical plus O double bond O gave rise to ROO radical. As the new radical cannot continue the chain gets terminated. Thus, each oxygen molecule break a chain by combining with an alkyl radical and thus stop the formation of the thousand of molecule of alkyl halide. This naturally slows down the rate of reaction. Of course, when all the oxygen molecules have been used up, the reaction proceeds normally. Some important aspects of halogenation of alkane. We will now discuss some important and interesting aspects of halogenation of alkane. First, relative reactivities of halogen in halogenation of alkane. The order of reactivity of halogen in the various halogenation reactions of alkane have been found to be F2 less than Cl2 less than Br2 less than I2. In fact, in case of iodine, the reaction does not seem to take place at all. We would try to account for this observed order of reactivity by considering the energy changes during the chain initiating and propagating step in the reaction of particular alkane, say methane, with different halogen. Since energy of activation, E-activation, has not been measured for various steps, all of the reaction, the value of delta H for different steps derived from the bond dissociation energies would be of a lot of help to us. The values of delta H for each of the three most important steps during halogenation of methane with different halogen are as follows. Various steps. X2 give rise to 2x radical. Delta H for fluorine 159, for chlorine 242.5, for bromine 192.4, for iodine plus 151. Second step. X radical plus CH4 give rise to HX plus CH3 radical. Delta H for fluorine minus 133, for chlorine plus 4, for bromine plus 67, for iodine plus 138. Third step. CH3 radical plus X2 give rise to CH3X plus X radical. Delta H value for fluorine is minus 292, for chlorine minus 108, for bromine minus 100, for iodine minus 84. The first step merely involves the dissociation of halogen molecule and therefore delta H can be taken to be equal to E activation. Thus iodine having the least E activation should dissociate more rapidly, followed by fluorine, bromine and chlorine in this order. But this order of dissociation goes against the observed order of reactivity of the halogen. This means that the first step cannot be responsible for the observed order of reactivity. The third step involving the reaction of methyl radical with halogen is found to be exothermic in all the four cases and the value of delta H is nearly the same for chlorine, bromine and iodine. For all these reactions, E activation is expected to quite small and the actual values is possibly not more than a fraction of a kilojoule in any case. Thus, this step also cannot explain the observed reactivities as it appears to take place with equal ease in all the cases. Coming to the second step, which involves the abstraction of hydrogen of methane by a halogen atom, we observe a wide variation in the values of delta H. The values of E activation for this step are found to be 17 kJ and 75 kJ respectively for reaction involving chlorine and bromine atom. In case of highly exothermic reaction with fluorine atom, the E activation is expected to be very low, about 1 to 2 kJ, while for highly endothermic reaction with iodine at atom, E activation must naturally be at least 138 kJ. This implies that the fraction of effective collision in this step should be in the order fluorine greater than chlorine, greater than bromine, greater than iodine. In this fraction of effective collision which control the overall reaction, for instance, the actual fraction of effective collision between chlorine atom and methane is found to be 1 in 40 at 548 Kelvin, while it is in 1 in 10 million in case of bromine atom and methane at the same temperature. Due to the very small fraction of its effective collision with methane, it is quite likely that bromine atom may happen to collide against another bromine atom or a methyl radical during its search for atom may happen to collide against another bromine atom or a methyl radical during its search for the properly orientated methane molecule for an effective collision with it. This means that a chain reaction involving a particular bromine atom may get terminated before long. It is found in actual practice that average chain length involving bromine is less than 100, while in case of chlorine it runs into several thousand. It is therefore evident that the rate of chlorination of methane and other alkanes should be much faster than bromination, in spite of the fact that the chlorine molecule dissociates into atom step 1 more slowly than bromine molecule. In case of fluorination, fluorine atoms are not only formed faster than chlorine or bromine atom due to lower reactivation of step 1, but also the length for reaction chain are much longer due to e-activation of step 2 being only about 1 to 2 kJ. At the same time, the overall fluorination reaction is highly exothermic, delta H being minus 427, minus 104.5 and minus 34.5 kJ respectively in case of overall process of the fluorination, chlorination and bromination. All these factors taken together justify the explosive nature of fluorination of alkane. For iodination to be carried out, E-activation for second step must be at least 138 kJ. Even with this value, the fraction of effective collision between methane and iodine atom works out to be 1 in 10 to power 12 at 548 Kelvin. Evidently, this is too low a fraction to allow any reaction propagating chains to function. That is why iodination takes place only at a negligible rate, even though iodine atoms are formed from their molecules at a comparatively faster rate due to low reactivation of step 1. It may be noted that the most vital step in halogenation, it means step 2, involves the formation of halogen acid. Now the bond dissociation energy of HF, HCl, HBr and HI are 569, 430, 368 and 297 kJ mole inverse. The order of hydrogen-halogen bond strength, it may be seen, is same as the order of reactivity of halogen in halogenation of alkanes. This indicates that the reactivity of halogen towards alkane is linked with the strength of hydrogen-halogen bond. The more the strength of hydrogen-halogen bond, the more the reactivity of halogen in the halogenation of alkanes. Further, the strength of hydrogen-halogen bond determines the stability of halogen acid. Therefore, it may also be stated that more the stability of halogen acid formed during halogenation, more is the reactivity of halogen. To conclude this discussion, it may be emphasized that most important and the rate determining step in halogenation of alkane is the chain propagating step. It is also to be noted that overall halogenation of alkanes except iodination proceed at quite a fast rate, even though the E-activation for the chain initiating step is quite high. This is because the decomposition of even one molecule of halogenation led to the formation of many molecules of alkyl halide due to the repetition of step 2 and 3 time and again. Thus, the overall reaction works out to be quite fast in spite of initially slow dissociation of halogens. Transition state for halogenation. It has been already stated that the vital step in halogenation of alkane is RH plus X radical give rise to R radical plus HX. The energy of activation for this step, which controls the overall process, is obviously equal to the difference in energy between the reactant and the transition state. Let us have a close look at this transition state, the formation of which is so important for the progress of halogenation. In this transition state, the carbon-hydrogen bond of alkane is somewhat stretched but not completely broken, while a new hydrogen-halogen bond has been partially formed. At the same time, the odd electron, which is on halogen in case of reactant and on alkyl group in case of product, is divided between the two in the transition state. For depicting such a state, dotted lines may be used for indicating partially broken and partially formed bond, while the symbol delta may be employed for representing each atom's share of odd electron as shown below. RH plus X radical reactant give rise to R dotted line H dotted line X transition state give rise to R radical plus HX product. The transition state leading to the formation of a particular free radical has some of the properties of the free radical. Thus, the free radical and the corresponding transition state have the same order of stability and ease of formation. Relative reactivities of alkanes in halogenation and relative reactivities of different classes of hydrogen atom. If a mixture of equimolar amount of two or more alkane is allowed to react with a limited quantity of chlorine or bromine, the product obtained consists of a mixture of different alkyl halide corresponding to the alkanes taken, but the relative quantities of alkyl halide in the mixture are not the same. This means that different alkane exhibits different degree of reactivity while reactivity with a particular halogen. These relative reactivities of alkane can be attributed to the reactivities of different classes of hydrogen atom present in them. It has been found that irrespective of the alkane in which they are present, the relative reactivities of hydrogen follow the order tertiary, greater than secondary, greater than primary. The hydrogen of methane being lesser reactive than even primary hydrogen. To have an idea of the magnitude of difference in the reactivities of different hydrogen atom, let us consider the reaction between a mixture of equimolar amount of ethane and methane and a small quantity of chlorine at 298 Kelvin in the presence of light. It is found that the amount of ethyl chloride formed is about 400 times as much as that of methyl chloride. CH4 plus CH3CH3 in the presence of Cl2 298 Kelvin light give rise to CH3CH2Cl 400 parts plus CH3Cl 1 part. This means that ethane is 400 times as reactive as methane, allowing for that fact that ethane contains 6 hydrogen atoms while methane has only 4. Each primary hydrogen of ethane is still about 267 times 400 into 4 by 6 as reactive as each hydrogen of methane. The relative reactivities of different classes of hydrogen atom may be explained by considering the relative stabilities of alkyl radical formed in the step which control the overall process of halogenation. For instance, in case of chlorination of methane and ethane, the respective rate controlling step may be written as CH4 plus Cl radical give rise to CH3 radical plus HCl. CH3CH3 plus Cl radical give rise to CH3CH2 radical plus HCl. Relative to the respective parent alkene, ethyl radical, a primary radical, is more stable than the methyl radical. As such, the transition state leading to the formation of this radical must be more stable than the transition state generating methyl radical. Consequently, the transition state of ethyl radical must have lesser reactivation than the transition state of methyl radical. Therefore, the transition state in the former case must be formed but more readily than the later. In other words, the carbon-hydrogen bond in ethane gets stretched and ultimately break more readily than the carbon-hydrogen bond in methane. That is why primary hydrogen atom in ethane are said to be more reactive than the hydrogen atom in methane. Similarly, the still greater reactivities of secondary and tertiary hydrogen atom can be explained in the term of greater stabilities of secondary and tertiary alkyl radical. Thus, it may be concluded that reactivities of different classes of hydrogen atom which determine the relative rate of halogenation of different alkanes follow the same order as that of the relative stabilities of corresponding alkyl radical, tertiary greater than secondary greater than primary greater than methane. Orientation of halogenation. It has been observed that sometimes a compound can form different products on reaction with the same reagent. This means that the compound has more than one reactive sites where the attack by the given reagent can take place. The process of determining the particular site or sites in the molecule where the reaction is most likely to occur is known as orientation. It involves the examination of factors which can influence the relative rate of competing reactions. For the present, let us consider the orientation of halogenation of alkanes. It has been pointed out earlier that the halogenation of higher alkene can lead to the formation of two or more isomeric products. For instance, the chlorination of propane at room temperature produces a mixture of N-propyl chloride CH3CH2CH2Cl and isopropyl chloride CH3CHCl in the ratio 45:55. The rate controlling step for the two competing reaction involves the formation of N-propyl and isopropyl radical by the abstraction of primary or secondary hydrogen of propane as shown below. Naturally, the relative quantities of two halide products would depend upon the relative rates at which N-propyl and isopropyl radicals are formed. Let us examine the various factors: collision frequency, probability factor, and energy factor which can influence the rate of formation of these radicals. First, collision frequency. As far as the collision frequency is concerned, it must be same for two reactions since the same particles. Propane molecule and chlorine atom are involved in each cases. Second, probability factor. The probability factor concerns the orientation of propane molecule at the time of attack by chlorine atom. For the formation of N-propyl radical, the propane molecule must be so oriented at the time of collision that the chlorine atom strike against the primary hydrogen which get abstracted. Similarly, the formation of isopropyl radical would require the propane molecule to be so orientated that the chlorine atom collide against the secondary hydrogen which get abstracted. Now there are 6 primary and 2 secondary hydrogen in each case of propane. Therefore, the probability factor should favor the formation of N-propyl radical by the abstraction of hydrogen in the ratio of 6:2 or 3:1. Third, energy factor. It is evident that the combined effect of collision frequency and the probability factor would require the formation of N-propyl chloride and isopropyl chloride in the ratio of 3:1. However, the actual ratio of the product formed is 45:55 or roughly 1:1. The proportions of isopropyl chloride is thus obtained 3 times the expected value. This means that about 3 times as many collisions with secondary hydrogen are effective as compared to the collision with primary hydrogen. This is quite in keeping with the influence of energy factor. Since isopropyl radical, a secondary radical, is more stable than N-propyl radical, a primary radical, the transition state leading to the formation of former radical must also be more stable and therefore have lesser energy of activation. In other words, E activation for the abstraction of secondary hydrogen and consequent formation of isopropyl radical is lesser than for the abstraction of primary hydrogen and formation of N-propyl radical. That is why the formation of isopropyl chloride take place preferentially. Similarly, investigations involving chlorination of other alkane indicate that the relative proportions of various isomeric chlorination products are related to the E activation for the abstraction of different classes of hydrogen atom and the formation of corresponding alkyl radical. In general, the rate of abstraction of hydrogen atom and the formation of corresponding free radical is found to be follow the order tertiary greater than secondary greater than primary. In fact, during chlorination at room temperature, the relative values of rate of abstraction for tertiary, secondary and primary hydrogen atom have been found to be 5:3.8:1 per hydrogen. It is interesting to note that relative values of rate of abstraction of hydrogens also depend upon the nature of halogen used, as explained in the next section. Thus, the relative values of rate of abstraction of tertiary, secondary and primary hydrogen in bromination at 400 Kelvin have been found to be 600 1600 ratio 82 ratio 1. These are clearly quite different from the values in case of chlorination. Knowing the probability factor and relative values of rate of abstraction of different hydrogen, or in other words their relative reactivities, it is possible to predict the ratio of isomeric halogenation product obtained from the given alkane. For example, in the chlorination of N-butane, the relative amount of monochloro product formed may be calculated as follows. N-butane in the presence of Cl2, a room temperature or light, give rise to two products, N-butyl chloride plus HCl, abstraction of 1 degree hydrogen, and second product is secondary butyl chloride, abstraction of 2 degree hydrogen. N-butyl chloride divided by secondary butyl chloride is equals to number of 1 degree hydrogen divided by number of 2 degree hydrogens into reactivity of 1 degree hydrogen divided by reactivity of 2 degree hydrogen is equals to 6 by 4 into 1 by 3.8 is equals to 6 divided by 15.2. The expected ratios of two products calculated above is equivalent to 28% of N-butyl chloride and 72% of secondary butyl chloride. The actual percentage is found to be the same. Reactivity and selectivity, chlorination versus bromination. It has been studied earlier that the halogenation reaction of alkane chlorine is more reactive than bromine. It has also been discussed that in case of alkane containing different type of hydrogen atom, the ease of abstraction or reactivity of different type of hydrogen follow the order 3 ratio 3 degree greater than 2 degree greater than 1 degree, irrespective of the nature of halogen taking part in the reaction. But now we consider a very interesting observation with the help of a simple example. When propane is subjected to chlorination, N-propyl chloride and isopropyl chloride are formed in the ratio 45:55. But when propane undergo bromination, N-propyl bromide and isopropyl bromide are formed in the ratio 4:96. Keeping in view the number of primary and secondary hydrogen 6 and 2 respectively, it is clear that secondary hydrogen of propane are more reactive than primary hydrogen in both the cases. But there is much more selective abstraction of secondary hydrogen in bromination than in chlorination. In general, the relative rate of abstraction of tertiary, secondary and primary hydrogen of alkane in chlorination at room temperature are 5.0 ratio 3.8 ratio 1, while in bromination at 400 Kelvin the relative rates are 1600 ratio 82 ratio 1. This means that bromine is less reactive than more selective in its reaction with different type of hydrogens. On the other hand, chlorine is more reactive but less selective. This is in accordance with reactivity selectivity principle, according to which if the attacking species is more reactive, it will be less selective, while a less reactive species is more selective. To understand the above principle, let us consider the transition state involved in the rate controlling step. It means attack of halogen-free radical on alkane, of chlorination and bromination of alkane. The reaction of highly reactive chlorine atom with alkane has very low E activation, and therefore the transition state is reached quite early when the alkyl radical character has just started developing. Therefore, the stability of alkyl radical ultimately formed does not have much effect on the ease of occurrence of the reaction. RH plus C radical, highly reactive, give rise to R radical, dotted line H radical, dotted line Cl radical. Reached quite early, alkyl radical character just beginning to develop, give rise to R radical plus HCl. In case of much less reactive bromine atom, the above step involves high E activation. As such, transition state is reached very late when sufficient alkyl radical character has already developed. Therefore, the transition state resembles the ultimately formed free radical in its stability and ease of formation. 3 degree greater than 2 degree greater than 1 degree. RH plus Br radical, low reactivity, give rise to R radical, dotted line H, dotted line Br radical. Reaches quite late, alkyl radical character sufficiently developed, give rise to R radical plus HBr. In other words, bromine atom will attack the tertiary hydrogen relatively much more easily than secondary, which in turn would be attacked more easily than primary hydrogen. Hence, as compared with other more reactive chlorine, there will be much more selectivity in the reaction with less reactive bromine. Interconversions of alkane. During the study of organic chemistry, we are often required to prepare one organic compound from other. Sometimes it may involve preparation of higher member of the class of compound from a lower member, stepping up a series, or vice versa, stepping down the series. We now illustrate the procedure followed by considering the interconversion of alkene. First, preparing a higher alkene from a lower member. This involves the following step. First, chlorination or bromination of given alkene into monochloro derivative. Second, Wood's reaction or Corey-House reaction of the monochloro derivative obtained with a suitable. For example, methane may be converted into ethane as follows. CH4 in the presence of Cl2HV give rise to CH3Cl. In the presence of sodium diether, Wood's reaction give rise to CH3CH3. Ethane may be converted into propane as follows. CH3CH3 in the presence of Cl2 light gave rise to CH3CH2Cl. In the presence of CH3 twice CuLi, Corey-House reaction gave rise to CH3CH2CH3. Second, preparing a lower alkane from a higher one. This involves the following step. First, conversion of given alkane into alkyl halide. Second, hydrolysis of alkyl halide obtained to get an alcohol. Third, oxidation of alcohol from into carboxylic acid. Fourth, decarboxylation of acid via its sodium salt to form the alkane. For example, ethane may be converted into methane as follows. CH3CH3 give in the presence of Cl2HV give rise to CH3CH2Cl. In the presence of aqueous NaOH, give rise to CH3CH2OH. Oxidation in the presence of K2Cr2O7 by H2SO4 give rise to CH3COOH. In the presence of NaOH, give rise to CH3COONa. In the presence of NaOH plus CaO, heat then give rise to CH4. Thank you.